So I'll try talking about chapter 2, section 1. So mainly I'm planning to talk about the derivation of the wave equation from the practical case of wide-varied string in one-dimensional case, and then I'll just briefly go over the higher dimensional case. So we're considering or talking about vibration in space RK. And then the R string, the two ends of R strings are at 0 and at
What
E1.
is L? E1?
Yes.
Oh, E1 is the basis in RK, right?
Yes.
Okay.
Yes.
And L is the length, okay.
That's the notation used. And then
But
here,
E1 is a vector, so it's not right to write it, but anyway, we understand.
Okay.
Okay.
And our
So
the vibration are
the ends are fixed, right?
yes, yes,
So
tied
you
down.
have the boundary conditions, they remain fixed.
Yes, tied down. This end.
Okay.
And then our vibration or displacement is controlled by the function utx, where t is the time and r, and x is 0. And what I can see from here, that this is a scalar, and we are looking at the one directional component of the vector in RK.
Well, if it only changes in that interval, then it doesn't depend on any other coordinates, right? In RK.
But
So what's the point of doing it in RK if this is only t is in R and x is in 0?
this function takes values in RK.
So it's not a string then. You said, okay, I get it now. So why didn't you write this that u is in RK? So u is a vector.
Yes, and u takes values.
So why don't you have a picture like for three-dimensional case? Just have a picture, label the axis 1 to 3, and show us where the string is and what this u means.
So we're looking at this direction here.
Well, just say 1 to 3. I mean, this is the first axis, right?
Yes.
Okay, just put in this 1 to 3. So which is that? Well, this is just label those axes.
Okay. This is 1, 2, 3.
Okay, and so where is your string? Where are those points where it is fixed? Here and here. Okay, so this is, and then just draw some string, which is why well, that's kind of. So that thing is a vector. Well, let me. You don't like. Okay, so here is x, right? Well, it's better to say this is x1 basically. So your u depends on x1. And so depending on x1, you have that function, you have that vector. And this vector could be anywhere, I mean, okay? So, and that's why this u, that's what this u is. The u is a vector, it's there. And that depends on t and x1. Is that clear? Because it could be just in this plane, or it could, it could have any configuration. So it just loose string in free space in general in K space. So depending on that, you have some vector, some variation. Okay.
And this u as the boundary condition is t0 and 0, and u t
should be 0, the last one.
This one?
Yeah, if you type it. Why there's only 1? You said it's a type, right?
That's what was said in the one. It says,
Oh, okay, then yeah, it's a little different vector. It's not,
can I have that?
it's not, well, it's this vector, because then that's this vector, so at every point. You see what I'm saying? At this point, you have this vector, and that's what he said. Okay, so at this point, there's that vector, at this point, there's another vector, and so on. But of course, you assume that, well, it cannot have that shape. It's going to be so that for each x1, there is a well-defined vector. Okay.
So, well, this is the boundary condition, and then he first found the kinetic energy here, that is generated by the displacement of the string. So, it was,
No, let me, excuse me for interrupting. Let me just to clarify what that u is. For any fixed t, for a fixed t, u is the map from, well, basically from the interval 0L to RK. It's this map, okay? So it's basically embedding of an interval in RK. So it's a piece of, it's a curve in RK, and that's, if you want, you could take for any fixed t. If you add t, of course you would get another copy of R.
so from the formula for kinetic energy here, it's the velocity. So for the displacement utx, the velocity is u, the partial derivative of t.
What is m?
The mass,
Mass of what?
mass of the string.
Of the whole string?
No, a very small portion.
Of which part?
Oh, he says that this string is uniform of mass density.
So this is mass density.
No, it's the mass.
Mass
It's-
of what then? Well, you have uniform mass density, you have a
Well,
lot.
if you say that this is the string,
Okay,
and then for according to some partition,
okay.
we are looking at a very small portion of it.
Okay, how small? I mean, of length, what, delta? And then.
Yeah, I can say, well, that's.
Okay, go ahead and then you'll see what it,
Delta L,
Just-
and then
or delta L?
or this.
Okay, and so that's the mass of that interval, okay.
This is not the mass.
I know, I'm saying that
Yes,
M is
yes.
the mass of the string of length delta
Yes.
L. So the whole mass of the string is M
Comes
times
to an
L.
integral.
Yeah,
Yes.
okay.
So then, the kinetic energy is out of the math, and it can go 0 to L, because I am going to add all those small parts of it, and then t length squared
So
dx.
that T of course is partial derivative, it's the velocity. With respect to T.
And then for,
I hope everybody understands that this is vector, that's a vector square, that's the absolute value of the vector, the length of the vector, okay.
and now for, from time t0 to t1, for a time period, for t0 to t1, we have the integral, for the t that is t0 to t1. I have the whole kinetic energy, which is from,
What is J0?
this is the kinetic energy.
Or what is T? You said T is kinetic energy.
So this is the kinetic energy from t0 to t1, but this is for a particular time.
Well, then it's not the kinetic energy, it's kind of work or something when you integrate it, right? So he calls this kinetic energy J0,
Yes.
and T also kinetic energy?
Well, I do not really understand the physics there, but he takes the integral of this over T0 to T, and then comes up with this one.
Okay, good. I think T is the kinetic energy, and this is, well, you could call it energy functional, it's an action basically, but that's not the kinetic energy. But anyway, just some functional, go ahead. Well, suppose that T does not depend on T. Okay, then T is constant, then J0 would be T times capital T times the length of the interval, or time interval, so that's not the kinetic energy. That's kinetic energy times time, so that's called action in mechanics, but it's just the name. Okay.
So would that be the same with the expression that I derived with the,
Well, it's the same.
potential energy? Because he used that again in deriving the potential energy too.
There is nothing wrong with it, I'm just saying that this J0 is not the kinetic energy.
Okay, it's the action.
Yeah, it's called the action. Well, the action is the whole thing. This is the part of the action that is determined by kinetic energy.
And as for the potential energy, he used Hooke's law, where it says that the potential energy in a small piece of string is a function of degree that the string has been stretched.
Mm-hmm.
So normally he says for the potential energy, he has T. Just 0 to L. Again, this is the sum. F Ux Tx, where F is a function depending on Ux as a variable or the directional displacement of the string.
So it doesn't say what function, just some function. Max of first is partial derivative.
It takes,
Yeah, well, I mean explicitly, it doesn't say what kind of function.
no,
So arbitrary function. What is, it depends on the properties of the spring, so properties of the material of the spring.
not that I can find. He didn't say anything on that.
Well, if you use Hooke's law, then it will be quadratic function of that, of Ux squared basically. But if you use something else, then it will be some other function. I think later on he takes it as a quadratic function. Anyway, go ahead.
Yeah, that's what I'm going to talk about because he mentioned that the quadratic